talk about sampling distributions. So, just to review. So say I give a very hard test to my pre-calc students and I measure the time it takes them to finish the test. We know from past experience that the time to finish the test are approximately normally distributed with a mean of 73 minutes and a standard deviation of 14 minutes. Suppose a randomly selected student takes 90 minutes to finish the test. Is this unusual? Should we be surprised? So if we find the z-score for this one student who takes 90 minutes, right? 90 minus 73 over 14, right? This is our x minus mu over sigma. That was a sigma. Would be 17 over 14, which is 1.21. So a z-score of 1.21. And our rule of thumb is that anything more than 2 standard deviations away from the mean is considered unusual. So one student taking 90 minutes to finish the test, not unusual. Now, in a period, an entire class period of students, what would you expect to be the average time it takes students to finish the test? It should be 73 minutes, right? If the second period is representative of all students, and we're assuming that it is, then the average time it would take second period to finish the test should be equal to the average of the time it takes all students to finish the test. The standard deviation here is a little bit trickier. We don't have a good intuitive rule for the standard deviation of a sample, of a sampling distribution so far. But what would you expect it to be greater than 14, less than 14, equal to 14? Think about it. So now, suppose that these 10 students take an average of 90 minutes to finish the test. Is this unusual? Yeah, right? We're expecting our average to be 73 minutes. So an average of 90 is much more unusual than one student taking 90 minutes. Can we conclude that this means there's something going on with second period, causing them to take longer to finish their tests, or might our results just be due to luck? In order to do that, we would have to find the standard deviation of the sampling distribution, which we're going to talk about in a minute. But just think about it, intuitively, if this group of 10 takes an average of 90 minutes to finish the test, do you think that could just be due to luck, or do you think something else is going on? Okay. So if we take a random sample of 10 students and find the average time it takes them to finish the test, we're going to get some number x bar. X bar is our sample mean. In the example that we had, our x bar was 90 minutes. If we take a different random sample of 10 students, this is assuming this is not just the 10 students in second period, but 10 students out of, say, all of the pre-calc students I've ever had. If we take a different random sample of 10 students, we're going to get a different x bar. If we take all possible samples of 10 students, find the average time it takes them to complete the test, and plot those times on a histogram, we create a sampling distribution. So sampling distribution is the distribution of the statistic for all possible samples of size n. In this case, n equals 10. So, all possible averages for all possible groups of 10 students. We can also do this with proportions. We will work on proportions probably in a week or so. But suppose we ask 20 randomly selected American voters who they voted for president in the 2020 election. We can calculate the proportion who voted for a certain candidate. If we take an infinite number of samples of 20 people, or all possible samples of 20 people out of the population, and plot the proportions on a histogram, we get the sampling distribution of the proportion. So, what does the sampling distribution look like if the population distribution is normal? So, this is pretty easy. If our population distribution is normal, our sampling distribution is also going to be approximately normal, which is handy for lots of reasons. If our population distribution is uniform, our sampling distribution is also normal. Weird, but very handy. And it's because for any symmetric distribution, you're going to get an approximately normal sampling distribution. Because there are more ways to get these middle values than there are to get values on the ends. For example, we could, if you were to roll 2 dice and average the numbers, right? 1 die roll is a uniform distribution. You have equal probability of getting each of the numbers on a die. But if you were to take all 36 possibilities of 2 die rolls and plot them, they start to look approximately normal. And if I feel like it, I will edit this video to include what that looks like. We'll see. So, real quick, this is the distribution of the sample mean of 2 dice. So, if we roll 1 die, and then we roll second die, and we add those 2 up and divide by 2, and we find the average. If we do that for all possible pairs of 2 dice, this is what the sampling distribution is going to look like. And so you can see from the chart that there are many more ways to get an average of 3.5 than there are ways to get an average of 6 or ways to get an average of 1. So we get a sampling distribution that is symmetric and is kind of normal looking. As our sample size gets bigger, we get a more normal distribution, but you can see that it is symmetric and has more of the means in the middle of the distribution. And also, we can show that this is an unbiased estimator because the mean of the sampling distribution is 3.5, and the mean of rolling 2 dice is going to be 3.5, the mean of this distribution. If you add all these numbers up and divide by 36, you're going to get a mean of 3.5 as well. So this is just an illustration of what I was talking about when I said that you're more likely to get values in the middle, right? You have one die has a uniform distribution, right? The population, you have a 1/6 probability of a 1 and a 1/6 probability of a 2 and a 1/6 probability of a 3 and a 4 and a 5 and a 6. So this is a uniform distribution, but when we sample take a sample size of 2 from the distribution and we find the average, we get a distribution that is not uniform. It is more normal looking because we have more extreme values that can balance each other out and give us values that are closer to the mean. So, if your population distribution is uniform, then you still get a normal sampling distribution. If the population distribution is skewed, depends on the size of your sample, right? If your population is like very strongly skewed, your sampling distribution may also be skewed. But usually it looks a little bit more normal. For large enough N, you do get a sampling distribution that is approximately normal. So for skewed distributions, it depends on the size of the sample. So, right? One roll of a die is a uniform distribution. Suppose we roll 5 dice and find the average. What will this distribution look like? So I did this with technology. And so here, this is a simulation. It is simulating rolling 5 dice and finding the average of those 5 numbers and plotting them and making a histogram. And you can see the histogram here starts to look approximately normal. And if we have it count, how many are greater than 5.2, none of them for however many samples I did. But here, having it add more and more, we're up to getting up to 500. We get, when we've done this 500 times, we get 8 out of 500. So, just out of however many I did the first time, I think it's 50, something like that, or 100, we didn't get any that are greater than 5.2. If we do it enough times, we get a few. We got 8 out of 500. Right? And this is a sample size of 5. So, rolling 5 dice, taking the average, how likely are we to get ones that are greater than 5.2? Right? So, do you think that these are fair dice? Right? What's the probability of getting an average of 5.2 or more from rolling 5 dice? We got 8 out of 500, which is a probability of 0.016. So, with fair dice, there's a 1.6% chance of getting an average of 5.2 just through random chance. So, if we do this once, you take 5 dice and you roll them and you get an average of 5.2, do you think that these are fair dice? They could be, right? Because it can happen, but it's very unlikely. So, I maybe would start to question those dice. Obviously, we can't we can't be sure of anything based on just one dice roll, but I would be a little bit skeptical. What if we roll 10 dice instead of 5 dice? So here's the same thing with a sample size of 10. And so if we do 100 rolls of these 10 dice, the number of times we get something greater than 5.2 is 1 out of 100. If I do enough samples, I do this to get up to 500, I still only have 1 out of 500. Right? So this was 8 out of 500, this was 1 out of 500. So 1 out of 500 times I get an average of 5.2 or more. That's 0.002. That's really unlikely. If I rolled 10 dice and got an average of 5.2, I would be really skeptical. Just because the likelihood of getting that just due to random chance is so very, very small. So, is what we just did a sampling distribution? No. A sampling distribution is a distribution of the mean for all possible samples of 5 dice. All possible ways that we could roll 5 dice. This is a distribution of our simulation results. But it does mimic a sampling distribution if we do enough dice rolls. Vocab. Some of these should be familiar from Unit 1. A parameter is a number that describes a population. A statistic is a number that describes a sample. We use statistics to approximate or estimate a population. Sampling distribution is the distribution of the statistic for all possible samples of size n. An unbiased estimator is when the mean of the sampling distribution is equal to the mean of the population. The mean, standard deviation, proportion are all unbiased estimators. The mean of that sampling distribution will be equal to the mean of the population. A biased estimator is when the mean of the sampling distribution is not equal to the mean of the population. And again, we talked about this when we did the Beyonce activity, right? When we randomly sampled words, we got a distribution where the mean of that distribution was the mean of the actual number of letters of the words in the song. When we picked words ourselves, we got a mean that was different. And that is the intro to sampling distributions. Stay tuned next time for more about sampling distributions. I gotta come up with funnier ways to end these videos. If you can think of things that would be funny, let me know.